Recall that one of the characteristics of a logarithmic function is that its domain is from 0 to positive infinity. If the value of the base is greater than 0, we have an increasing logarithmic function, and if the value of the base is a fraction, we would end up with a decreasing logarithmic function. But for the moment, let's focus on this scenario. And let's also use the base value of 2 to have a brief conversation about the algebraic reason why the domain has to be greater than 0. Let's consider for a moment trying to plug in a negative quantity. And let's replace the functional notation so that it's a little easier for us to convert to exponential form. When converting to exponential form, we'd have 2 raised to the y power is equal to negative 1. And this is where we see that this isn't possible. There's no power that we can put on 2 to have an output that is a negative quantity. Even if we raise it to a negative quantity, we get positive outputs. When we raise 2 to the 0 power, we get a positive output. And certainly when we raise 2 to the positive powers, we get positive outputs. So it's not possible to get a negative quantity here, and therefore we cannot have a negative value in the argument of a logarithm. Before we move forward, I'd like for you to notice that this logarithmic function has not had any transformations. The domain is from 0 to positive infinity because we haven't moved this function to the left or to the right. But the idea that we want to move forward with is that the argument of a logarithm must be a positive quantity. Given the function f of x is equal to log base 4 of x plus 2, let's notice that this is going to be a transformation of that logarithmic function to the left 2 units. Let's first graph this function using transformations in order to visualize what the domain of this function will be. So we start with the basic function of log base 4 of x, and we've discussed the characteristics of this function, which is that it has a vertical asymptote of x is equal to 0, an x-intercept at 1, 0, and because the base of this logarithmic function is greater than 1, we're going to have an increasing logarithmic function that approaches that vertical asymptote but never actually gets there. So this is where we begin. The only transformation that we have here is that we're going to move everything to the left 2 units. And when we move to the left 2 units, that is going to take that vertical asymptote to the left 2, and it will then be located at x is equal to negative 2. We'll also take our x-intercept to the left 2 units, and this will now be located at negative 1, 0. And now our increasing logarithmic function approaches x is equal to negative 2, and the domain of this function is going to be from negative 2 to positive infinity. So the domain is now different because we shifted the whole thing left 2 units. Now, some logarithmic functions are difficult, if not impossible, to graph using transformations, so we also need an algebraic process. And again, we're going to bring back that idea that the argument of a logarithm must be positive. So in our logarithmic function, we're going to consider this argument, x plus 2, and figure out who are the x values that ensure that our argument is positive. So solve for x, we subtract 2 from both sides and get x is greater than negative 2, which of course is the same domain that we just generated using the graph. This process is also a good bit shorter and easier.